Welcome back, dear students. In this video, we are going to look at two other concepts that are frequent to non-contiguous memory allocation. And the first of them is virtual memory. And virtual memory is a paging mechanism that allows a program to use more memory addresses than are available in main memory. That we call virtual. So when they say it uses more, using more memory means that what the other memory are not like real. So that what we call it virtual memory. Or we can still define virtual memory as a technique that allows the execution of processes that may not be completely in memory. That's what we have. Now let us try and understand what virtual memory is all about. It is a method of using computer hard drive to provide extra memory for the computer. Segments of memory are stored on the hard drive known as pages. When a segment, because we know that what it is a physical memory that is being divided into pages. So it's a logical memory which is being divided into pages. When a segment of memory is requested that is not in memory, it is moved from the virtual memory to an actual memory address. The operating system manages virtual memory address spaces and the assignment of real memory to virtual memory. Address translation hardware in the CPU, often referred to as memory management unit. So the memory management unit is is the address translation hardware in the CPU, and it automatically translates virtual addresses to physical addresses. Virtual memory allows for effective multiprogramming and relieves the user from unnecessarily tight constraints of main memory. So what we need to understand here is that segments of memory are stored on the hard drive. They are known as pages. And when a segment of memory is requested that it is not in memory, it is moved now from the virtual memory to the actual memory address. And this is done by the memory management unit. So you need to know that the concept of virtual memory here is mostly done by the memory management unit and the operating system. And the main advantage of this memory of virtual memory is that it ensures multi-programming and it relieves the user from unnecessary tight constraints of main memory because it gives the impression that we have a large main memory whereas it is not the case. Virtual memory is commonly implemented by demand paging, which is the concept we are going to see. It can also be implemented in a segmentation system. Demand segmentation can also be used to provide virtual memory, but we are going to stick on demand paging. Demand paging system is similar to a paging system with swapping. So is that what we usually say demand paging is paging plus swapping. Generally, a process resides on secondary memory, which is the disk. When we want to execute a process, we swap it into memory. We saw all of this when we were doing we saw swapping. Rather than swapping the entire process into memory, it swaps the required page. This can be done by a lazy swapper. So what we are saying is that what we saw in swapping that we saw these two different terms. We saw loading and swapping, and we said that loading is when we are moving from the disk to the main memory, and swapping is either from the disk to the main memory or the main memory to the disk, where we have swapping and swap out. But now we are saying here that what instead of swapping the whole process out of the main memory for other processes to be executed, we only swap a particular page to enable other processes to use the amount of main memory liberated. And this is done by a lazy swapper. And a lazy swapper never swaps a page into memory unless that page will be needed. So it does the swapping only if it is needed. A swapper manipulates entire process while a pager is concerned with the individual pages of a process. So what are we saying here? Swapping, as you can see, where we are performing a different movement, because we said that swap in is when we are moving a process from the backing store to the main memory, and swap out is when we are moving from main memory to the backing store. If we associate that with paging, what we saw in the last two previous video, we are going to result to what we call demand paging, whereby the swapping is of the different pages that are being done. So we are swapping by what different pages that we call demand paging. Now, performance of demand paging. If we let P be the probability of a page fault, we saw a page fault, we saw that it's the interrupt which occurs when we are making reference to an invalid page, then the effective access time will be calculated as using the formula. So to calculate the effective access time of a particular demand page, demand paging, sorry, is going to be 1 minus P times the memory access time plus P times the page fault time. But this is just a formula. In any case, we are faced with three major components of the page fault service time: the service, the page fault interrupt, to read in the page, and to restart the process. So these are the three cases we are faced with when it comes to the page fault. So the page fault can occur during the service of the page fault interrupt, when reading the page, and when restarting a process. In the next video, we are going to talk about an important concept, which is page replacement. We shall go further to look at the different algorithms used in performing page replacement. An example to better explain how these different algorithms work. Do not forget to like, to subscribe, and to share. And see you in the next video.